Welcome folks, our first video on applications of integrals. In this video, we're going to be talking about area. Our discussion of area is going to be generally similar to what we're going to do throughout these applications of integrals. Throughout these applications of integrals, we'll be trying to find some quantity. We'll approximate the value of that quantity with a sum. We'll see how we can make that approximation exact by letting the number of approximates go to infinity. Accordingly, our sum will become an integral. So everything here is taking essentially a Riemann sum and relating it to the definite integral. Start by reminding you of the original motivation for the definite integral, that is area problem. So the area problem, simply stated, is find the area of the region R between the x-axis and the graph of the function f on the interval from a to b. So we saw that one strategy to do this is to divide the interval from a to b up into n subintervals of equal width, raise a rectangle on each of those subintervals whose area approximates the area of the according strip, and then let the number of rectangles go to infinity. As the number of rectangles goes to infinity, the approximation becomes exact, and this limit of a Riemann sum becomes a definite integral. So the sum becomes an integral, the x sub i's become x's, the delta x's become dx's. So the question that we want to answer for today is, what about other areas? What about other areas? So what about an area that's not just the area between the x-axis and a curve on the interval from a to b? So we'll start with the following problem, a new area problem. The goal of this new area problem is to find the area A of some region R that's bound between two curves, say f and g, on the interval from a to b. And we'll formulate our approximation to this problem the same way, namely divide the interval from a to b up into n subintervals with delta x, estimate the area of each strip with the area of a rectangle, add up those areas of rectangles to approximate the area of the region, and then let the number of approximations go to infinity in order to make that approximation exact. So accordingly, the area is approximately the sum I equals 1 to n of f of x sub I minus g of x sub I delta x. So here we see the area of that ith rectangle, just the width times the height. The height is f minus g, evaluated x sub I, and the width is delta x. Add up those n areas and let n go to infinity. As n goes to infinity, the sum becomes an integral from a to b. The x sub i's become x's, and the delta x becomes dx. And again, the x sub I star here is a bit of a technicality. It turns out that as n goes to infinity, you can pick your representative point in the interval to be any value between x sub I minus 1 and x sub I, and that's what x sub I star represents. We'll just go ahead and take it to be x sub I because we're not going to worry about that technicality. Okay, so illustrating this strategy with a specific example, we'll try to find the area bound between two curves, y equals 3x minus x squared and y equals x squared minus x over the interval from 0 to 1. So this problem is framed exactly as the motivating example, namely find the area between f and g on the interval from a to b. Now we don't have graphs of these functions, but sketching these is something you should be able to do. Both functions are parabolas, and we know that, or both functions are quadratics, excuse me, and we know that the graph of quadratics are just parabolas. The first one opens down and the second one opens up. Factoring those parabolas makes it a little bit easier to see where those intercepts are. The first has intercepts at 0 and 3. The second has intercepts at 0 and 1. And here are those graphs. So the area we seek to find, again, is the area between the x-axis, the parabolas on the interval from 0 to 1. So here's that area, and here's a crude sketch of a rectangle on that area. So again, our strategy, which we don't need to go through in its entirety, is to Again, here's one of those rectangles. You can see the area of that rectangle is going to be the top curve minus the bottom curve. That's the height times the width, delta x. Divide the interval from a to b, in this case 0 to 1, into n subintervals of equal width. Divide up, raise a rectangle on each subinterval. Add up all of those areas from 1 to n, and that's a good approximation of the area of the region. So here you see f and g evaluated at x sub I. So this again is the area of the ith rectangle times delta x, the width. Add those up from 1 to n. As n goes to infinity, this approximation becomes exact. Of course, as n goes to infinity, the sum becomes an integral from 0 to 1 in this case. The x sub i's become x's, and the delta x becomes a dx. And now this is an integral we can evaluate with the fundamental theorem of calculus. So start by simplifying the integrand. 3x minus x squared minus the quantity x squared minus x, distribute the minus sign, obtain 2x minus 2x squared. Power rule for antiderivatives gives us x squared over 2 and x cubed over 3. Evaluate between 0 and 1, and I'll leave off those details and allow you to work on them on your own. And we find that that area is 1/3. So I'll go ahead and express this truly as an area with 1/3 units squared. Maybe these graphs are in inches or centimeters or something like that, but for the time being, we'll just have 1/3 units squared. Okay, variations on the same theme include a couple different ideas. Different twists include maybe you're just told a region with no explicit bounds given. It might be more convenient to slice horizontally with thickness delta y instead of thickness delta x. And also the top and the bottom curve might switch, which we'll need to be aware of. So just a few examples to illustrate those variations. Here's the first one. Let R be the region bounded by the graph of the quadratic y equals 12 minus x squared and the graph of the other quadratic y equals x squared minus 6. We'll just go ahead and write down a definite integral representing the area of this region. So the first thing we'll have to do is sketch a region, and just like before, here we have two parabolas. The first one opens down and the second one opens up, and the 6 and the 12 respectively shift them around a little bit. So here's a graph of those two parabolas. And you can see that, that the first one is a parabola that opens down and is shifted up by 12. And the second one is a parabola that opens up and is shifted down by 6. Now, of course, we'll need to find the intersection of these points, which you can sort of eyeball from the graph, but in general, you might not know that. So we'll go ahead and do that by just solving a quick algebraic equation where the graphs intersect. So those points of intersection are where 12 minus x squared is equal to x squared minus 6. Just solve algebraically for x equals 3 or minus 3. Okay, so again, in the back of our mind, what we're doing here is on this interval from minus 3 to 3, dividing the interval up into n subintervals of equal width, raising a rectangle on each subinterval whose area estimates the area of the strip, finding the area of that rectangle, adding up the area of those n rectangles, and then letting n go to infinity. So we'll do that here quickly with some x sub i's and n going to infinity. So again, here's our rectangle, ith rectangle with area quantity 12 minus x squared minus the quantity x sub I squared minus 6 times delta x, width times the height. The approximate area is the sum of those n areas. As n goes to infinity, we're left with the definite integral from minus 3 to 3 of the quantity 12 minus x squared minus the quantity x squared minus 6 all times dx. And I'll point out that you can use a little bit of symmetry here. We have even functions on a symmetric interval, so we can express this integral in terms of the integral from 0 to 3 instead. So here's that symmetry argument expressing the integral as twice on the interval from -3 to 3 as twice the integral from 0 to 3. I've simplified the integrand here, and I won't go through the details, but you can quickly use fundamental theorem of calculus to find that that value is 72 square units. Okay, another example here. Let R be the region bound between y equals x minus 5, a line this time, and x equals y squared minus 3y. The goal is to find a definite integral representing the area of the region R. So in this case, as you can imagine, it's pretty quick to draw a line. The first line is just the line with slope 1 and intercept minus 5. The second curve, though, is a little bit trickier because it's x in terms of y. So this is a parabola that actually opens to the right. And again, by factoring, you can see where those y-intercepts are at 0 and 3. So here are the graphs of those two functions, the line and the parabola. And accordingly, we want to find the area of the region bound between those graphs. So excusing the inaccuracy of the green, the area is roughly that green. And in this case, as you might imagine, it makes sense to take a slice in the other direction. So to take a slice with thickness delta y. Now, as you can imagine, slicing with thickness delta y eventually tells us we'll have an integral in terms of delta y. That tells us we need all of our graphs in terms of y also. So I'll do that here, expressing the graph on the right, the line, as x equals y plus 5. And then, of course, the other graph, the parabola, is already in terms of y. So again, thinking about dividing some interval up into subintervals of thickness delta y, the area of the ith rectangle is going to be y sub I plus 5 minus the quantity y sub I squared minus 3y sub I times delta y. Add up those n rectangles, let n go to infinity. We'll be left with a definite integral, but we do need to find those intersections. And of course, the curves intersect where the graphs are equal. So again, setting those graphs equal, those functions equal, we can see that they intersect when y is equal to 5 and y is equal to minus 1. So just add up the n areas, let n go to infinity, and we're left with a definite integral. So the approximation of the area is given by this Riemann sum. As n goes to infinity, this approximation becomes exact, and the sum, of course, becomes an integral from minus 1 to 5. Those were the y values we solved for on the intersection. Minus 1 to 5 of the quantity y plus 5 minus the quantity y squared minus 3y. Of course, this integral isn't so hard to evaluate, and you can quickly come up with the value. But in this problem, we're actually just asked to find a definite integral representation, so we can stop here. Okay, one final example here, the area of the region between the curves sine of x and cosine of 2x on the interval from 0 to pi over 4. So we'll go ahead and find a definite integral representation without the use of the absolute value. It turns out you can always use absolute value to do this, but we want to find one without the use of absolute value that represents this area. So again, we'll start with a sketch of the graphs of these two functions, sine of x and cosine of 2x. Of course, the sine function is the one that starts at 0 at 0. It has period 2 pi. The cosine of 2x function is the one that starts at 1 when x is 0. And of course, because it's cosine of 2x, it has period of pi instead. So here we see those two graphs, the cosine curve in green and the sine curve in blue, and we're interested in the area between the curves on the interval from 0 to pi over 4. And I think I'm going to make a quick adjustment here on the fly and go ahead. Oh yeah, I can leave that at 0 to pi over 4. So pi over 4 is approximately here about 0.75 or so, a little bit bigger than that, and we can see that the area is given by that shaded area. Now on this interval, of course, the top and bottom's curves change. So we'll need to go ahead and solve for this point of intersection here to see where those top and bottom's curves change in order to write the integral actually as, write the area as two integrals. So the curves intersect where the functions are equal, and we'll use one of our handy trigonometric identities to identify where those things are equal. So here's this short calculation for when those graphs are equal. They're equal when sine of x is cosine of 2x. Using a half angle identity, we see that that's where sine of x is 1 minus 2 times sine squared of x. We can factor this quadratic in sine to see that we need to solve for sine of x equals 1/2 or sine of x equals -1. There are, of course, a whole bunch of points that this happens, and we're only interested in the first one, which is at x equals pi over 6. So similar idea here, we'll go ahead and find the first area, then the second area, and then add those up using pi over 6 as a dividing line. So here are those two areas, and again, I've eliminated the delta x's and x sub i's, but the area of the first region is top minus bottom dx integrated from 0 to pi over 6. And the area of the second region is top minus bottom dx integrated from pi over 6 to pi over 4. Now, of course, the top and bottom switch, and that's sort of the difficulty in this problem, giving us the integral for the total area, which is actually given by the sum of these two integrals below. Now we could go ahead and just use fundamental theorem of calculus to find those values. But again, here we're just asked to find an integral representation for that area. Okay, folks, hope you've enjoyed this video on areas. Have a great day, and we'll see you next time. Bye-bye.